Okay, so Physics 11, we're going to be continuing with our work on Newton's laws today, looking at some other forces. Specifically, we're going to focus on forces of friction. But before we even really do that, there's something that I wanted to kind of bring to your attention if perhaps you wanted better visuals from our last lesson on Newton's laws, just to kind of get an idea of what's going on there. So just to kind of show you here, there's a great little online simulation, and you'll be able to see it here through my screen recording. But the website's there, so if you wanted to take a look at some of these things that we've been dealing with like forces and motion, one of the concepts we talked about last lesson was the idea of a net force, right, where there can be multiple forces acting on a single object, and that can cause an overall net force. And this simulation can kind of show you that, right? And they can show you all these values of your sum of your forces and all the values and the speed at which things happen, right? So you can apply, particular people, right? And as you do that, you can see that there's a right force here being applied of 100 newtons, and then the sum is also 100 newtons. But if we place another person here, now all of a sudden there's a left force of 50, and now the sum of the forces with the net force is only 50. And then if we were to hit go, right, we see that the speed is slowly increasing, right? So we are accelerating in the right direction, okay? Again, you could kind of play around with this again to see kind of what happens here. I mean, if it's even, right, our sum of forces is 0 and nothing is moving, right, and we have no speed. Again, we could play with it a little bit here as well, where perhaps we really increase the right force, right, and we see our sum of forces is largely to the right. And when we go, we see that speed is increasing a lot faster, right? So the more force we're applying, we're seeing that the speed picks up, and we do see that larger acceleration there, okay? So that was kind of that idea of net force, right? How you do opposing forces, and then the sum of the forces is what's going to help you calculate your mass times acceleration values using our F equals ma, okay? You can also take a look at it in the terms of just motion in general, right, when we're applying a force to something, right? So here you could kind of play around here and see, okay, well, if this is our person applying a particular force of, let's say, about 100 newtons or so, right, using Newton's second law, right, where that object in motion stays in motion, once you've applied that force, it keeps going at a constant speed, right? If there's no other forces acting on it, it's just going to keep on going, right? But what we could do is notice how if we continue to apply that force of around 100 newtons and kind of hold it there, we do see that our speed up in the corner there is increasing, so we have an acceleration happening, right? It's when we stop applying the force that our speed then remains constant, right? And that's where we're at, right? So as we continue to apply that force, it does increase the speed. The other thing, again, you can start noticing is that if we were to increase that mass, right? So if we take this 100 kilogram garbage can, so now the mass is a lot larger, and if we apply the same amount of force around that 100 newtons, notice that our speed is still increasing, but a lot slower, right? Because the larger the mass, right? Because that's that relationship of force is equal to mass times acceleration. It's now due to the mass being larger and the force remaining the same, we don't get the same acceleration, right? Because there's a difference there, okay? And again, you could kind of keep playing around with that. Then you could increase the force, you could lower the mass and kind of see what happens there, right? So again, we could take both of these things off, just put the low mass on there. I'll have to refresh that. Right, so take that one off, put the smaller mass on there, and apply a much larger force, right? And we see that accelerated quite quickly, right? Oh. Okay, so again, you see that kind of maxes out, okay? So just kind of to show you that there is that relationship between mass and acceleration. What we're actually going to be focusing on today, and this has a nice little application here as well, is the idea of friction. Right, so not all surfaces are frictionless, and that results in, the object actually slowing down. So as you can see here is if we again show all of our things, right now we have like a medium amount of friction. Again, we can change that value. We'll keep it with the, all right, so if we have no friction, right, you can kind of see that it looks like ice. And if we apply that force, right, it will move, okay? But then as soon as we let it go, right, again, it keeps moving because it's a frictionless surface. However, if we increase our amount of friction, right, if we increase the amount of friction and then apply that force, right, notice how right now the applied force and the friction force are equal and the sum is 0, and that's resulting in no motion. So what happens is, in order to be able to get that object to move, you actually have to apply enough force to overcome the force of friction that's kind of keeping it in place. So slowly, there we go, we've kind of reached that sweet spot, right? So now we've applied this force of 170, now we're up to, let's say, closer to 200 newtons, right? And the friction force was 94 newtons, and we are able to get a sum, like a net force of that 107 newtons, and we do get something moving. If we let it go and we stop applying that force, right, you notice how our object is slowing down, the speed is decreasing, right? It's now decelerating because the only force at play is friction, and that's what's slowing it down, okay? So again, that kind of continues to happen. You could, again, change it so that there's a lot of friction, right? And if we keep the mass the same, you'll now notice, right, around 200 newtons before, we were able to get the object moving. Now we're having to apply more than that, right? Because we've increased the amount of friction, so we have to have a lot more applied force in order to get it moving around the same, have the same acceleration and speed. And then once again, it will actually slow down faster because the force of friction is a lot stronger, okay? So that's kind of the general idea of what we're getting into with the rest of our lesson today, but feel free to kind of, if your computer's able to, I've included that little simulation website there. Feel free to just kind of play around with that to get a better idea as to the connections between all of the different types of, connection between mass and force applied and friction, just to help you out with that, okay? All right, so obviously when we're talking about an object sliding across a surface, there are actually two types of friction that might be acting on it. You've got what's called static frictional force and kinetic frictional force. There's a difference between them. Static frictional force is that frictional force that exists when you start to move an object from rest. So again, you notice there in that simulation that we started applying a force, but it took a while before we actually were able to apply enough force that it started to move. Okay, so that would have been that frictional force that we needed to be able to overcome in order to get the object starting to move. Okay, then what we have is a kinetic frictional force, which is that frictional force that exists while an object is already moving. All right, and that would have been after it's already moving. What's the force of friction being applied there? Okay, now what you have is, depending on the surface, right, and the surface on object on surface, there's different what we call coefficients of friction. Right, these are just constant values that are used in our calculations. Okay, so their symbol is this kind of like U-looking shape. It's not a true U; it's actually the symbol mu. So it's kind of like, looks like U with a little bit of a tail. Okay, and again, you'll notice that the coefficients of friction do actually change in terms of static versus kinetic, right? So it's like the frictional force to get it moving is, as you'll notice, larger than the coefficient of kinetic friction once it is actually already moving, right? So again, you can see these, if you've got rubber on dry solid surfaces, you've got between 1 to 4 here, and then with kinetic it's just 1. With rubber on dry concrete, 1 changes to 0.8. Okay, and then you just kind of look through that table. So some of the questions you'll be asked to reference this table. Sometimes they just tell you the coefficient of friction directly, right? And then sometimes, due to our equation that we'll talk about today, you'll actually be asked to calculate it, right? So again, you'll notice that, things like even ice on ice, there is still a slight coefficient of friction there, but even like lubricated ball bearings, there's very, very minimal friction because you want them moving smoothly, okay? All right, so when we talk about being able to calculate a frictional force, one of the things we need to go back and discuss is that idea of normal force. Okay, we talked about that in our last lesson, where normal force was the force that's perpendicular to the surface on which the object is resting. Okay, now if something is resting on a horizontal surface, like we see here, this book is just resting on a horizontal surface. Okay, so since it's resting here, perpendicular to that would be going straight up, right? Now, in any sort of horizontal laying situation, you've got the force of gravity that will be pulling it down, which can be calculated just needing to know the mass of the object and whatever the force of gravity is on that planet. So if it's Earth, it's just your 9.81. okay? But then your normal force would be equal but opposite, right? Because if this is not actually falling, it's just resting on that surface, the normal force would just be equal to what the force of gravity would have been, okay? Like I said, we could change this, and if we were to kind of rotate this image, and like let's say we were pressing the book up against the wall, well then it's resting vertically, so the normal force would actually be acting out, right, instead of acting up. Okay, but a lot of things is more pushing things in on a flat surface than it is about holding it up against a vertical surface. All right, so that's typically given by F subscript N, right, so normal force, okay? And that leads us to that actual surface friction formulas. So in order to calculate what the force of friction is acting on an object, right, you need to take the coefficient of friction, right, which is a constant and there's no units associated with that, okay, and then you multiply it by the normal force, right? So what you end up getting is normal force measured in newtons multiplied by just a constant with no units, giving you still force of friction in newtons, okay? So that's what's going on for calculating that. So again, you see that mu letter, that's the coefficient of friction that you use. You multiply by your normal force, and that will give you your force of friction in that particular object, right? So we'll go through quite a few practice problems again today, just kind of showing how we would calculate, you know, various aspects of friction, and then I will again show you how, you know, the idea of net force is coming through with some of these questions as well. All right, so let's start with this one. So during the winter, owners of pickup trucks often place sandbags in the rear of their vehicles. Calculate the increased static force of friction between the rubber tires and wet concrete resulting from the addition of 2.00 times 10 squared kilograms of sandbags in the back of the truck, right? So essentially what you're doing is you're increasing the mass of the object, which will therefore increase your force of friction, all right? So let's take a look at how we would calculate that. So we're just being asked to figure out calculating the increased static force of friction. So we don't actually know the mass of the truck. We don't know the initial force of friction, but we just want to know what it's increasing by. And we know that it's increasing by this additional mass of this 200 kilograms of sand, right? So we can just figure out what that force of friction is using that value, okay? So if we do that, angle up here. Okay, so one of the things we first needed to look at was the coefficient of friction based on the question was on wet concrete, right? Rubber tires on wet concrete. And when we look that up, right, in our table, and it was static, right? So from starting, not the kinetic, we got that the coefficient of friction static for that was 0.70. Okay, and again, that was just being looked up. Now we know that the formula for force of friction is that coefficient of friction times our normal force. So again, we might want to draw anything with forces, draw a free body diagram. So what we have is a mass, right? And what's happening is, you know, it's not moving, so there's nothing pulling it right or left. However, there is still gravity acting on it, so force of gravity would be pulling it straight down, and your normal force would be acting opposite. Again, since it's not moving, these would be equal. All right, so if something's in motion, right, and you kind of saw that again in that little simulation, if something is in motion to the right, there's more forces being applied this way than there are this way. If something's in motion going up, there's more forces being applied here than there are being applied down, right? But if something's not moving, then all of your forces are just kind of in equilibrium and nothing's happening, right? So again, we can calculate here our force of gravity pulling down, which would be a negative force, and then our normal force would be the same value but positive, okay? So what we'll do is we'll kind of do that sidebar and say, okay, well, our force of gravity is mass times gravity. So that was the 2.00 times 10 squared kilograms, and that'd be multiplied by our negative 9.81 meters per second squared. Okay, and I'm using the negative value there because the force is pulling down. Okay, so we have a force of gravity that ends up equaling negative 1,962 newtons. Okay, and like I said, because it's not moving, our normal force is going to be equal to our force of gravity, but in the opposite direction. So if this is negative 1962, then our Fn is a positive 1962 newtons. Okay, and now our normal force is what we use to find our force of friction. So now our force of friction is that value of 0.7, right, that coefficient of friction, multiplied by our 1962. newtons, which was our normal force. And then that means that our force of friction is 1.37 times 10 cubed newtons, right? So I think it becomes like 1373, but we only get 3 sig figs in this question, right, due to the 2.00 kilograms, right? 2.00 times 10 squared kilograms. So this is our increased force of friction, okay? So whatever the force of friction was before adding the sandbags, we're not sure. However, once we add the sandbags, we can add this much friction, right? So just kind of adding more friction to be able to get things started, right? And obviously it's for winter so that you've got better traction. Okay, so that's kind of that first straightforward one. Okay, let's look at our next example. So again, there you go. All right, so example 2. So a horizontal force of 85 newtons is required to pull a child in a sled at a constant speed over dry snow to overcome the force of friction. Okay. The child and sled have a combined mass of 52 kilograms. Calculate the coefficient of kinetic friction between the sled and the snow. Okay, so in this case, we don't know that coefficient of friction, right? That is what we're actually trying to find here. Okay, now again, notice that it's kinetic friction, so it's assumed that we're already moving. It's not overcoming. It's not what is it to overcome. It's what is it to keep it moving at a constant speed. Okay, now something again to note is when we talked about, force equaling mass times acceleration, right? If something's moving at a constant, something's moving at a constant speed, you've basically just been able to just overcome that force, and then you just kind of maintain that speed, right? So you're not applying any extra forces there. Okay, so they kind of need to balance out, right? Because if you're applying an extra force on one side, you're going to have acceleration, right? So because this question is talking about it needing to be at a constant speed, right? Basically what we're saying is that our applied force and our force of friction would need to be equal, okay? So what we would do here, go back, okay? So again, we have a force being applied. So again, if we draw that free body diagram, right, you've got this mass here that has a mass of 52 kilograms of the child in the sled, right? You're applying a force this way, pulling it, right? And then there's the force of friction pulling it back, okay? Like I said, with force being mass times acceleration, if this was much larger, this object would be accelerating. Okay, so if the force of friction is larger than, if the applied force was larger than the force of friction, then our object would be accelerating in this right direction, right, and speeding up. But because it's being done at a constant speed, again, things are in equilibrium, and because we've already overcame the force of friction, right, because we're talking about the kinetic force at this point, right, the kinetic coefficient of friction, these two values would actually need to be equal. Okay, so so we were given actually that the applied force was 85 newtons, right? So we also know that the force of friction was also 85 newtons, okay? Would have to be. All right, yeah, they would have to be equal, right? Just because they're staying in that same, staying at the constant speed. Okay, so again, remembering we're being asked for mu, right? We're being asked for what is the coefficient of friction here. So if we think about that formula where our force of friction is equal to our coefficient of friction times our normal force. So to just get this by itself, we would need to divide both sides by the normal force. So force of friction divided by the normal force will give us that coefficient of friction that we're looking at. So again, like I said, we know that the force of friction that we need to overcome, or is in order to maintain that constant speed, is that 85 newtons. That's not a problem. But the other thing we need is what is our normal force. So again, remember your normal force would be acting perpendicular to the surface, right? So we're not being pulled up a hill, we're just being pulled along straight snow. So what's happening is that you do have force of gravity this way, and your normal force would be this way, okay? Again, they would actually be equal because we're not moving up or moving down, right? So we could calculate force of gravity there and say, right, well, our force of gravity is our mass times our 9.81. The mass was 52 kilograms multiplied by that negative 9.81 meters per second squared, which gives us a force of gravity of negative 510.2 newtons, which means that my normal force, right, is equal but opposite here. So it's a positive 510.2 newtons. Right, so now going back to this question that we had started, well, then our force of friction divided by our normal force is our coefficient. So force of friction was 85, right, because it is like at a constant speed. And now we're going to divide it by our normal force, which is of 510.2 newtons. And then that gives us a value of 0.167. But in terms of sig figs, we only get 2, so we would have to call this 0.17 instead. Okay, so that would be the coefficient of kinetic friction, right, to keep things moving at a constant speed, right? So like I said, if after we've overcome it and we keep applying a larger force, we would be accelerating, right? But because we're going at a constant speed, we know that these values have to be the same. Okay. All right, let's move on to sample problem number 3. All right, so again, you see that same kind of thing, right? The force of friction is 85, it's implied because 85 newtons overcomes the friction, right? And it's constant. We have all those values. We see us calculating the force of gravity, which is equal but opposite to the normal force. Do the division. There you go. All right, so let's take a look at number 3. So on a newly discovered planet, it is determined that ice sliding over ice has a coefficient of friction of 0.329, okay, which is very different from that other slide that we saw on Earth, right, where ice on ice was actually either 0.1 for static friction or 0.03. So clearly there's something happening on this planet, okay? It's much, much larger. Okay, so if 91.2 newtons of force are required to move a 21.5 kilogram block of ice across an ice field at a constant velocity, determine the acceleration due to gravity on this planet. Okay, so a few things here. I'm going to just start writing down those key values before I switch to the video. All right, so we do have the applied force that's happening there, right? So we have our applied force here at 91.2 newtons. And again, notice that it's moving it at a constant velocity. So if it's moving at a constant velocity, that means that that applied force is also going to equal our force of friction. Okay, so we've got that. Then we also have that the coefficient of friction is 0.329, 0.329. And we also have that the mass of the ice block is 21.5 kilograms. Now we're actually looking for what's the acceleration due to gravity on this planet. All right, so going back here. All right, you're in the shot, Jersey. Move out of the way. There you go. Okay, so we go back to our status, right? Again, you want to look at your free body diagram. All right, so once again, here's our mass of our ice block. We're applying a force to push it. We have the force of friction pulling backwards, and again, because it's moving at a constant speed, these values are equal, right? So that's your 91.2 newtons, but this is also 91.2 newtons, okay? And then, again, we would have your normal force acting here, and you'd have your force of gravity acting here, okay? Now, typically, we'd be able to find the force of gravity no problem, just mass times acceleration due to gravity, but we're not on Earth, so I can't just multiply by 9.81. That's the thing that we're trying to find, okay? So instead, we set up something slightly different, right? So remember that our force of gravity, yeah, that would equal mass times gravity there, right? That would be what was happening, okay? But we don't have that. But we also know that Jersey, you can't have that on while I'm doing this.
Mommy, sorry.
I know, sorry, but you just can't have your sound on while I'm trying to do this. Sorry,
Okay.
students. Okay. So your force of gravity, we knew would be mass times the acceleration due to gravity, but we don't have that because we're not on Earth right now. Okay? But we know that these two things would be equal as well. So remember, normal force came into play as well using that force of friction formula, where our force of friction was equal to our coefficient of friction multiplied by our normal force. And what's great about this is because we were given the coefficient of friction and we know the force of friction, we can actually find our normal force by dividing force of friction by our coefficient, right? So we can take our force of friction divided by mu and get what our normal force would be. So we can take that value of 91.2 and divide it by the 0.329. Right, so 91.2 newtons divided by 0.329, and we get a normal force value of, I've misplaced that number. Okay, so 91.2 divided by 0.329, so that gives us a normal force of 277.2 newtons. Right, so again, remember that your force of gravity and your normal force are equal but opposite, right? So that would mean that your force of gravity was going to be negative 277.2 newtons. We have the mass of the object, of the ice block, is 21.5 kilograms. And then what we're trying to find here is that value of G. Right? So now, to get G, we just divide both sides by 21.5. So we can take that negative 277.2, divide it by the 21.5, and what we get is negative 12.9 meters per second squared is the acceleration due to gravity on this particular planet. Okay, so you end up being able to use a combination of what you know about all the different forces, right? Again, so constant speed, these have to be equal, so you know, even though we are told the applied force, that means you can get the force of friction, right? Then you've got the coefficient of friction given to you, right? Again, you know that your normal force and your force of gravity should be equal but opposite, right? And just kind of piecing all those things together, you can kind of work backwards to figure out what that force of gravity is supposed to be, okay? All right, so what we'll do is, right, so again, you kind of see that process written out there, right? So again, you see that force of friction as the 91.2 is implied because it's at a constant speed, okay? Again, you solve for that normal force due to your force of friction formula, right? You know that your normal force is the same as your force of gravity, and away you go. Okay, so this again would have been if we were in class. I'd give you a few minutes to try this one on your own, but because we're not in class, I'm just going to again do this for you. If you do want to pause this and try this one on your own, you can, but there are a couple other extra things kind of happening here, so you might just want to hold off. All right, so in this one, you have a 6.2 kilogram object is being pulled along a horizontal surface by a force of 22 newtons. If its acceleration is 1.1 meters per second squared, what is the coefficient of friction between the two surfaces? So the big difference in this one is that it's not being pulled, something's not being pulled at a constant speed or constant velocity, it has acceleration, which means there is some sort of net force happening, right? It means that our applied force is bigger than our force of friction. So once again, start by drawing that free body diagram of what's happening here. Okay, so again, listen what we have. So we know that the mass is 6.2 kilograms. We knew that there was an applied force of 22 newtons, and we knew that the acceleration was 1.1 meters per second squared, and we were looking for the coefficient of friction, right? Let me just double check those. Yeah, so pulled along a horizontal surface by a force of 22 newtons, acceleration, there we go. Okay, so essentially what's happening is that here's our mass, right? It's being pulled along a horizontal surface this way, right? There's our applied force of 22.0 newtons, okay? And we know that it has an acceleration of 1.1 meters per second squared, which means this must be larger than the force of friction. So we can just kind of show that arrow slightly smaller, right? So this is a case now where our force applied is not equal to our force of friction because we actually have acceleration happening, okay? So we have the other forces still acting on that particular mass. We still do have our force of gravity here, and we have our normal force here. Again, these would be equal but opposite because we're not moving up or down, so they would just be in balance, okay? Now, we can find our force of gravity, right, because we have the mass and we know we're on Earth, so we can solve for Fg by taking, right, our mass multiplied by our force of gravity. So that's our 6.2 kilograms multiplied by our negative 9.81 meters per second squared. And we get that our force of gravity is negative 60.8 newtons, which means that our normal force would be a positive 60.8 newtons. Okay? Now, the other thing we need to kind of keep in mind here is that again, because we have this acceleration, we have a net force that's happening here. Okay? So, when we're taking a look at this motion, right, there's this idea of, well, F net, right, any set of forces is equal to mass times acceleration. That's where that acceleration's coming in, okay? But what is that idea of, okay, well, what's our net force here, right? Well, we don't have anything moving in up or down, but we do have things happening right and left. And our net forces is the sum of the forces acting on the objects, right? These would just cancel each other out. But you do have an applied force that's going to be larger than the force of friction acting against it. So essentially what you have is a positive Fa minus your force of friction is equal to that mass times acceleration. We know the applied force here is 22 newtons, right? We know the mass of the object, and we know the acceleration, and that allows us to find force of friction. So all we need to do is move this negative force of friction over, bring the mass times acceleration over as well, so what we get is Fa minus Ma is equal to a positive force of friction. And then we can start plugging in those values of things we know, right? We know that our applied force was the 22 newtons. We know the mass of the object is 6.2 kilograms. We know the acceleration of the object is 1.1 meters per second squared. And all of that will give us that force of friction. So if we take 22 and we subtract 6.2 times 1.1, we get a value of 15.18. So I'm going to kind of reset over here. Okay, so now we have that our force of friction is equal to 15.18 newtons, right? And remember, the goal here was to find the coefficient of friction. And we know that the formula for force of friction is the coefficient of friction multiplied by the normal force. We now have a value we can plug in here for our force of friction of 15.18 newtons. We had our normal force calculated as 60.8 newtons. So to get our coefficient of friction, we just need to take our 15.18 and divide it by 60.8. Right, so we can take our 15.18 newtons, divide it by 60.8 newtons, okay, equals our coefficient, and that gives us a value of 0.25. Okay. So again, remember that if you are dealing with something that has an acceleration, it's not in constant, not at a constant velocity, you do need to make sure that you're looking at your F net, right? All of the forces acting together. If something is in fact moving, like accelerating, it means that there is like an unbalanced force situation there. So you need to look at your F net equation of mass times acceleration, right? Because I mean, if you are moving at a constant speed, then your acceleration is 0, meaning that your sum of all your forces is also going to be equal to 0, right? It's kind of, it all balances out. But because force is the mass times the acceleration, right? If there is acceleration, it means that there's an unbalance of forces somewhere, right? And you need to kind of take a look at that, right? It's why the free body diagram can certainly help, right? So in this case, because we were moving in a positive direction, right? Because we had positive acceleration given to us, we can say, okay, well, I'm moving this way, which means this has to be bigger than this, right? And in order to kind of calculate the sum of those forces, well, these would be 0, right? Because we're not moving up or down. And then your applied force minus your force of friction, right, would give you your sum of your forces, right? And then that allows you to kind of keep on working that way. Okay, so that's good old force of friction. So again, if you want even more extra visuals, right, there's another website here that I've included to help as well. So you've got the other one that I showed you, and then this one also has, this is the one we used, I think, for our graphs and stuff, right, where again, you can apply some more things here and they kind of show you the visual, even the graph of it, right? So like you can increase the mass of the object and you can just apply your force and go, right? And right, if there's no surface friction, it's just going to keep accelerating, right? The velocity is going up over time, okay? But then again, you can kind of change it where now if we increase our surface friction, right? So there's your coefficient of friction, right? You notice that you have an F net that's different, right? So again, if we reset, you can kind of take a look at that. So none, with those values staying the same, right? And you notice that your applied force is the F net, right? But as soon as we start increasing our surface friction, you see your F net has gone down significantly, right? You still are accelerating, right? In that case, because you're continuing to apply that force. But again, you notice that your F net has changed significantly once you've increased your force of friction. All right, so you can play around with that as well if you'd like. Okay, so that's everything there. You've got couple pages, couple questions from the textbook, as well as a worksheet, right? So as usual, I'll post the answers to all those as well, so you can kind of chip away at them and see how you're doing. Okay, and then we'll go from there.